The Sun, the closest star to Earth, is the foundation of life on our planet and has been the object of human fascination for millennia. Its immense energy powers the solar system and supports all life on Earth. Understanding the Sun involves delving into its origins, structure, life cycle, and its role in the broader cosmos. Let's explore the story of the Sun. 1. Formation of the Sun. 4.6 billion years ago. The Sun formed approximately 4.6 billion years ago from a vast cloud of gas and dust called the solar nebula. This nebula, mostly composed of hydrogen and helium, collapsed under its own gravity, triggering the process of nuclear fusion at its core. Solar nebula. The solar system began as a swirling cloud of gas and dust. The gravitational collapse of this cloud caused it to spin faster, flattening into a disk. Most of the material in this disk collected in the center, forming a protostar, which would eventually become the Sun. Nuclear fusion. As the gas and dust continued to collapse, the pressure and temperature at the core of the protostar increased dramatically. When the temperature reached around 15 million degrees Celsius, nuclear fusion ignited. Hydrogen atoms fused into helium, releasing vast amounts of energy, marking the birth of the Sun. 2. Structure of the Sun. The Sun is composed of several layers, each with distinct functions and characteristics. Core. The Sun's core is where nuclear fusion occurs. Temperatures here reach around 15 million degrees Celsius. It is the engine that powers the Sun, converting hydrogen into helium and releasing energy in the form of light and heat. Radiative zone. Surrounding the core is the radiative zone, where energy moves outward through radiation. This zone is incredibly dense, and photons, light particles, can take thousands of years to pass through it. Convective zone. Above the radiative zone, in the convective zone, energy is transferred by convection currents. Hot plasma rises to the surface, cools down, and then sinks back down to be reheated. Photosphere. This is the visible surface of the Sun, where light is emitted into space. The temperature here is around 5,500 degrees Celsius. The photosphere is what we see when we look at the Sun from Earth. Chromosphere. Above the photosphere lies the chromosphere, a reddish layer visible during solar eclipses. It's a dynamic region where solar flares and other phenomena occur. Corona. The Sun's outer atmosphere, called the corona, is a halo of gas extending millions of kilometers into space. Surprisingly, the corona is much hotter than the surface, with temperatures reaching over 1 million degrees Celsius. The corona is also the source of the solar wind, a stream of charged particles that flows through the solar system. 3. Energy production and nuclear fusion. At the heart of the Sun, nuclear fusion is the process that powers the star. This fusion occurs when hydrogen nuclei, protons, combine to form helium, releasing enormous amounts of energy. The energy travels from the core outward, taking thousands to millions of years to reach the surface and radiate into space as light and heat. Hydrogen to helium. The Sun primarily fuses hydrogen into helium through the proton-proton chain reaction. Each second, the Sun converts around 600 million tons of hydrogen into helium, releasing energy that sustains its glow. Mass energy equivalence. A small amount of mass is lost in this process and is converted into energy, as described by Einstein's famous equation E=mc². This energy powers the Sun and, by extension, life on Earth. 4. The Sun's impact on Earth. The Sun is essential to life on Earth, providing the energy necessary for photosynthesis, the process by which plants produce food. The Sun also drives the Earth's climate and weather systems, creating wind patterns, ocean currents, and the water cycle. Light and heat. The Sun's light provides warmth, making Earth habitable. Its energy helps maintain the balance of ecosystems, influencing weather patterns, seasons, and even the behavior of living organisms. Solar radiation. Besides visible light, the Sun emits ultraviolet, UV, radiation, which can be harmful in large amounts but also essential for processes like the production of vitamin D in humans. Earth's atmosphere, particularly the ozone layer, protects us from most of the harmful UV rays. Auroras. The Sun's influence extends beyond light and heat. Solar activity, like solar flares and coronal mass ejections, CMEs, can interact with Earth's magnetic field, producing stunning displays of auroras, known as the northern and southern lights. 5. Solar cycles and activity. The Sun undergoes an 11-year solar cycle, during which its activity levels rise and fall. This cycle is marked by the number of sunspots, dark, cooler regions on the Sun's surface where magnetic fields are particularly strong. Solar maximum. During periods of high activity, known as the solar maximum, the Sun exhibits more sunspots, solar flares, and CMEs. These eruptions can affect satellite communications, GPS systems, and even power grids on Earth. Solar minimum. Conversely, during the solar minimum, the Sun is quieter with fewer sunspots and reduced activity. This cycle affects the entire solar system, including the behavior of the solar wind and the intensity of cosmic rays reaching Earth. 6. The Sun's life cycle. Like all stars, the Sun has a finite lifespan. Currently, the Sun is about halfway through its main sequence stage, a period of stable fusion in which it burns hydrogen in its core. It has been in this phase for about 4.6 billion years and is expected to remain stable for another 5 billion years. Red giant phase. Once the Sun exhausts its hydrogen fuel in the core, it will begin fusing helium into heavier elements. This will cause the Sun to expand into a red giant, swelling to engulf the inner planets, possibly including Earth. The surface temperature will drop, giving the Sun a reddish hue. Planetary nebula and white dwarf. After the red giant phase, the Sun will shed its outer layers, forming a planetary nebula, a cloud of gas and dust that will drift into space. What remains will be the Sun's core, which will become a white dwarf, a dense, hot remnant that will slowly cool over billions of years. End of the Sun's life. Eventually, the white dwarf will fade, becoming a cold, dark black dwarf. However, this process will take trillions of years, far beyond the current age of the universe. 7. The Sun's place in the universe. The Sun is a relatively average star in the grand scale of the universe. It is classified as a G-type main sequence star, G-dwarf, one of many billions in our Milky Way galaxy. While not particularly large or bright compared to other stars, the Sun's proximity to Earth makes it vital to us. Solar System's anchor. The Sun's gravity holds the entire solar system in place, from the planets to comets and asteroids. Without the Sun, the planets would drift into space. Solar neighbors. The nearest star to the Sun is Proxima Centauri, about 4.24 light-years away. The Sun orbits the center of the Milky Way, taking about 225 to 250 million years to complete one orbit, a journey known as a galactic year. Final thoughts. The Sun is more than just the center of our solar system, it's the source of energy that makes life possible on Earth. From its formation in a cloud of gas and dust to its eventual death as a white dwarf, the Sun's story is a cosmic one, intricately tied to the existence and evolution of life on our planet.